Okay, hello everyone. I guess it's time to start. So today we'll be discussing a very interesting JEP. 461, also known as 485, because those names change along the way, and which I believe is one of the most exciting additions to the Stream API since 2014. My name is Grzegorz Piwowarek. I'm a Warsaw JAG user group lead. I am a leader of Waiver, open source project. I teach distributed systems, Java, Golang, and architecture. And today we'll be live coding some of the new exciting Java features. A small disclaimer, this presentation is AI assisted. So if AI starts swearing, we are all collectively responsible for that. So before we start, I'm not going to give you once again the introduction to Streams API, but we need to do a quick driver's license exam. So let's jump right into that. So Streams API is probably one of those things that you touch every day as a Java developer. So we have a stream of a couple of elements that's usually coming mostly from collections. And now you can do stuff with that. So if I try to map that and print it out, what we get is 1, 2, 3. Print it out quite easily using some declarative programming. However, what's quite important to recall is that there are two types of methods in Stream API. Intermediate and terminal ones. That's why let's try to redo this example. So as you can see, this is pretty easy. You are getting 1, 2, 3 printed out. But what if we drop the for each? Well, obviously, nothing gets printed out because there's no, printing out anywhere in there. But let's mix it up. So let's not do that. Let's try to print out the number exactly when we are trying to map it. So what do you think we'll see on the console if I run it? Nothing. Oh, perfect. Precisely, we are getting nothing because what we've done right now is we use an intermediate method and we've injected some unexpected side effect right in there. And intermediate methods, they don't trigger the consumption of a stream. They essentially change how the definition of a stream, but it doesn't really trigger any operations to happen. So if I wanted to actually print out all the elements of a stream, I would use a for each that I used earlier on, because that's a terminal operation that actually triggers the stream consumption, and guess what? Iterates through all the stream elements, as the name suggests. It executes a consumer instance for each stream element. And this caused a lot of trouble in the past, especially when Streams API started getting more advanced. So quite a common case I've seen a couple of times is that people tried to do some fancy operations in here, for example, hi, return E, and then call some terminal operation. What do you think we'll get here now if we try to run it? That's not so easy, right? So there are two answers to that. If you are running on ancient JDK 8 version, you are likely to see hi 3 times. Or perhaps to make it easier, let's just go for E. However, this is not guaranteed to happen because streams are able to ditch some of the operations if they are not likely to impact the final result. And guess what? Map operation can never impact the number of actual elements that go through a stream instance. So in JDK 9, an optimization was introduced, which made it something like this: never call. So the map operation actually is dropped along the way because, it can't impact the size of actual stream. And we know the size of a stream up front. If we call a filter in here, even if we use a filter that's neutral, that returns true for every operation, now it can't make this, it can't guess if the filter is going to filter out or not something. It's not inspecting the Lambda instance itself. That's why it returns stuff. So those are two fundamental ideas of Stream API. Yeah, there is a question. If you put filter after the map, okay, and what do you think would happen if we put a filter after a map? We can do that. At the end of the day, it also changes the number of stream elements. So in this case, it doesn't really change anything. Let's keep going, because this is not a 101 on Stream API. We are going to way more interesting things. So we have two types of stream operations, intermediate and terminal. So let's say we want to collect all stream elements to a list. And you're probably doing this all the time. Nothing fancy. Let's say you want to now collect all the stream elements into a set. Guess what? There is no method called toSet. What if I want to particularly collect the all stream elements into a hash set instance? Or perhaps a map, hash map, linked hash map, tree map. You would need to bloat the API service a lot to cover all of those. So Java folks came up with some really smart idea. They introduced the idea of collectors. Collector is a generic terminal method, which means that technically each collector goes through all stream elements and is able to produce arbitrary result of your choice. So for example, and I'm sure that folks that's been with Java for longer than 10 years know this, because actually that was the default way to collect everything into a list. And then they introduced shorthands for that. So in the past, you would need to go collect, collectors to list. And now you can, without bloating API surface, you can inject your own custom strategies. So, okay, good point. Okay, I hope you can see it now. So now, you can provide your own strategy that essentially tells Stream how to perform your own terminal operation. In this case, it's toList. Boring, right? You can do toSet. Boring. However, if you want to enforce one particular collection type, you can inject your own collection factory. For example, oh, that's a very bad example, Copilot. For example, an array list. Now, you have guarantees that this is an array list. So this concept is pretty powerful. So actually, a couple of years ago, I built a library called parallel collectors, and actually, this is leveraging, like stretching the concept of collectors to its limits, where you can essentially perform parallel computations at the collect stage. We'll get back to this later on, because one of the new methods is kind of relevant to that. However, it has one very big limitation. It can't short-circuit the stream. So whenever you are trying to write your own custom collector, there is nothing you can do. You always need to collect all stream elements. And guess what? If a stream is infinite, well, you have a trouble, because essentially you will be trying to collect everything. Obviously, you can skip some elements, but Stream will keep evaluating forever. So this is pretty bad. However, developers were requesting for quite a long time a new API methods to be added to streams. And those were not just terminal operations, but also intermediate ones. And that again, this is for Java developers, I mean, creators of Java language, not Java developers themselves. This is problematic because there are so many ideas, and you can't really put all of them into APIs because those become bloated and hard to navigate and use. So they were very hesitant when people said, okay, so there is this distinct method, but why can't I do distinct by a certain property, just like I can do with sorting, and so on and so on. And they were pushing back for a long time. We are not adding more methods, no more methods. But they reached a point where actually they figured out how to tackle it a different way. So the whole point of today's talk is to show you the new concept that's going into Streams API, and it's called a special method called gather. This is still a preview API. It's been in Java since Java 22. Now it's going through a second preview phase, and in March we can expect the GA release. As for now, because as you can know, things changed. So far, creators of Java were pretty stable when it comes to promoting preview features to GAs. But with string templates, there was a setback, so they removed it altogether, decided to change the design. But since we went through 2 iterations already, there are still people, they are still collecting feedback, but it's unlikely to change. At least I don't think in a major way. So what's the point? So the idea is to introduce a collect-like method with intermediate operation semantics. So if you translate that to Polish, it sounds more or less the same. But the idea is that collect is a terminal operation and gather is intermediate. With gather, you have an ability to signal to Stream API that you don't want to process any more elements. Additionally, you don't really get that much flexibility when it comes to return values. When it comes to collect, you can pick your own. You can collect to a collection, you can collect to a string, int, object, whatever you choose. But if you call a gather API, it's always stream of something. So if you make a decision so that your gatherer collects only to a single element, it will be still exposed as stream of something and not just this particular type that you want to return. And in a second, we'll dive into internals, how this looks like, how collectors look like, how gatherers look like, and we'll go through some of the already available gatherers. There are not so many because there are just 5, and then we'll try to write our own. So, for example, essentially, when you look at the anatomy of collector and gatherer, it's very, very similar. So, if we keep going, let's again create a stream of 1 to 3. Let's create a very, very simple collector that collects everything into a list, which is already available. So such a list collector would be a generic method that returns a collector instance that takes elements of type T, stores them temporarily in an array list, and returns a list T. Let's call that custom to list, and so on. And the whole trick of a collector is that you need to provide four methods. You need to provide a supplier. Supplier is essentially a point of initialization. So you need to create, streams need to know how to somehow create an instance of an intermediate representation. Then you need to provide it with a behavior that tells it how to consume a value, which essentially means how to take a value and put it inside an accumulator. Then you need to figure out a binary operator, which is a behavior that tells it how to combine two intermediate operations, two intermediate states. This is useful for parallel processing. However, function, and lastly, it's a finisher. So when you have an accumulator, you need to know how to put it together and just return. That's actually that's the output that you get from a collector. Plus some cool fancy methods that give you characteristics that give hints to Stream API how to optimize stuff. So let's try to do this. And the reason I'm showing you this is because Gather API is very similar, but with a couple of twists. So let's create our own to-list collector. So this is our to-do, but let's go for public static class custom to-list collector. It collects type T, implements collector of type T, array list T, a list T, and let's auto-generate everything. And it might be intimidating if you start from scratch, but after some time that's really easy. You need to create an empty accumulator. You need to figure out how to put, well, Copilot, this is not how it's supposed to be implemented, I believe. So you have an accumulator and type T, and you need to know how to put an element into it. Well, that's trivial. If you have two accumulators, you need to somehow be able to put them together. Okay, it's doing a good job now. And finally, you can just create a finisher that repackages the intermediate representation into a list. This is obviously suboptimal, but shows you the anatomy of a collector. So pretty much, when you start thinking about gatherers, it's something very, very similar. because the one thing we are missing is an ability to signal the stream termination to source. So if you look at the Gutterer interface, Gutterer, where is it? Where are you? Gutter downstream, where are you? That's a big Java doc. Okay, here you are. So essentially, Gutterer is very simple. It also has an initializer, which acts the same way as collectors. It has a special integrator, which is more or less, which is the trickier part. We'll get to this later. Same kind of combiner and also a finisher. Integrator is the fancy thing. It's the interface which has a method that keeps track of state, an element, and the downstream. When you think downstream, when you see downstream in Gutterer's API, think things from reactive Java or similar. That's pretty much a place where you put something inside, and if you put it there, it goes through the stream API. But you can also check if downstream is not rejecting elements. So as you can see, the API is more or less the same. So let's actually try to put this in use. So, but before we start implementing our own, let's see what we have already in there. So, as you can see, the Gutter method acts the same way as collect method, and all our predefined Gutterers instance are actually in the class called Gutterers. And you have something like window fixed, window sliding, fold, scan, and map concurrent. Let's try this window fixed, but in order to see this in action, we will need to see we use a bigger stream instance. So let's go for iterate. Let's start from scratch, from 0, and let's limit to, let's say, 20. And window, one of the predefined window Gutterers, they allow you pretty much to group all those stream elements into windows. So if I put a window size of 3 and try to print it out, that's what I'm getting. So as you can see, all of those stream elements going through it were grouped into windows and piped through stream. Technically, you could do it yourself in the past, but it'd be a bit tedious to do. And in most cases, you need to have access to the direct source of stream to make that happen. So there is a window fixed. Let's have a look at the second one. So there's also window sliding. Let's go to the fourth one. Window sliding, which acts almost the same way, but it slowly moves through the whole the sequence of elements. So as you can see, in this first instance over here, we start with 0, 1, 2. Then the next window starts at 3, which is not present in the first window. If you go to the next example and use apply sliding window, as you can see, there's overlap with a step of 1. At the moment, you can't configure the step size. It's always fixed to 1. I hope that's also the feedback I'm about to leave for the Gutterers creators, that perhaps we might be getting a special extra step parameter in here, because it sounds like a no-brainer. Another interesting one that we are getting pretty much out of the box is, please, Copilot, don't do this presentation for me. Let's take all of that again. Let's make it a bit shorter, maybe. Another one is fold. Fold is more like reduce. It acts more or less the same, with slightly different guarantees, because you can define your own combiner. So let's do that. And let's see what it prints out, but let's do 4 elements. So as you can see, we are starting from 0, 1, 2, 3, 4, and it's just summing all the elements. Actually, let's go 3. So it's 1, 1, 2, 3. However, as you can see, this is not much, doesn't give you that much extra value because you have reduce on stream as a terminal operation. However, there's another method called scan, and the scan method is a bit way more interesting because at the end of the day, it acts more or less the same way as fold, but it emits all the intermediate states along the way. So if you take last element of the scan operation, it's essentially equal to fold. So as you can see, it's going 1, 0, 1, 3, and those are all intermediate steps along the way. Because we've started with 0, we've accumulated 1, and then we added 2, which gave us 3. And if we were to sum all of that, that would be just that. So let's go for the fold. And that's 3, indeed. So as you can see, this is pretty convenient and helpful. However, I believe the most important addition to the Streams API is map concurrent, because that's something that Streams API craved for a very long time. Let's take a very simple stream of just 4 elements. Let's try to process it and store results in a list. But let's imagine that this processing is very, very slow. So, for example, we have process method that takes some value. It takes this value very slowly. Let's call it 1 minute, make it 1 second. And then returns it. So now, if we replace I with process I, this is going to take some time, more or less 4 seconds. In order to not do any guessing, let's quickly introduce a method that calculates that. Copilot is now actually helpful. So now we can enclose that in a runnable instance. And we should see that this took around 4 seconds to execute. Yep, that's milliseconds, so that's accurate. Let's actually print it out that those are milliseconds. So now, here comes Stream API, and with one of the most promising features. So Stream API promised us is that now we can stop learning concurrency and parallel programming, because all we need to do is to use just one simple keyword. And so as you can see, all we did now is that we introduced one single keyword, and now it's all running in exactly 1 second instead of 4 ones. So can we now ditch can we call ourselves performance engineers? Unfortunately not, because it turned out we don't have much time to dive into the whole problems of parallel streams, but it turned out that the thread pool that's used underneath, it's not very elastic. It's actually fork join pool, and in order to prove it to you, let's actually print it out. Come on, Copilot, you know you can do this. Yep, you did it. So now you can clearly see that it's running on fork join pool, common pool. And to make the long story short, this is just one static thread pool being kept in the JVM, which is limited in size. And it's limited in size because it's designed for CPU-heavy workloads. And there is no point in introducing higher parallelism level than the number of CPUs that you have. Because even if you add more, if you try to parallelize more, at the end of the day, those are physical cores that are running that. But you might be asking, but what's wrong with that? But it seems to work just fine. Okay, it seems to work just fine, and it's running under 1 second. But if there was someone to pollute the thread pool in some way, that wouldn't be that fun anymore. So, for example, what I can do is that I can create another stream where I'll be just sleeping forever. Integer max value. And now let's just return I. And if I run it specifically in another thread, because Stream API is blocking, so if I just block here, we'll never get here. Thread, I will just run start. I will sleep here for 100 milliseconds or something to give it enough time to pollute the original thread pool. And it's running fine. That's not how it's supposed to happen. So there's thread platform start. it's running on parallel thread pool, go here, for each system out print line. Thread sleep, give it a bit more. Yeah, it wasn't enough time. Oh no, it's running fine. What's going on in here? We start, Oh yeah, good point. Yeah, that's just 4, right? Good point, thank you. So what we are going to do here is that we are going to run on 20, because I don't have 20 cores in here, I believe. So now what's going on is that now all the parallel streams magic is gone, because all of the core thread pool was polluted with tasks that are blocking. So the foreground pool is busy doing nothing, precisely sleeping. And the performance of all my parallel streams is degraded, because as you can see, this is effectively all being performed on main. So for a very long time, actually for many years, creators of Java were hesitant to introduce any changes to that. So as you can see, when it comes to parallel, you can't provide your own thread pool or anything like that. And there's a good explanation for that, because at the end of the day, the parallel streams were designed to handle CPU-bound tasks, and they're internally optimized for that. So there is no point in injecting other types of thread pools. However, with gutterers, this changes. So if we go now and see another example, let's copy all of that and go here. But instead of parallel, we get rid of that and we introduce gather, and we use gutter's map concurrent. First big change, you can introduce max concurrency level. So it's your choice what's the concurrency level. With parallel streams, you can't do this. It's more or less, I mean, technically you can use a system property to change the parallelism level, but this is not very comfortable. And then you provide a mapper. And look what's going on right now. I'm not providing any executors at the moment. As you can see, it's clearly running somewhere. It looks like it's not running on anything, so maybe it's running in the cloud or something. However, this is virtual threads. So, and again, there's not enough time to go into concept of virtual threads, but in the day, those are threads that exist only at the JVM level, not at the operating system level, are very cheap. So therefore, it's very easy to create many instances of them and not worry about internal details of thread pool configuration, because virtual threads are essentially not pulled. You're just supposed to create them on the spot. And finally, you get parallel streams in a much easier and safe way. Because in the past, in most cases, using parallel streams of production could be not the best idea. Even if you were using them responsibly, and imagine you were deploying your application onto application server, you could be doing all the things right, but another team that's also writing code that's also deployed to the same application server could impact your code. Because at the end of the day, some application servers are JVM, simple JVM instances which have one static shared thread pool. So even it would be unsafe even when you are doing everything right. But here you go. There's a gutterer map concurrent. Unfortunately, you can't still choose your own thread pool, but this might come somewhere in the future. If not, you can use a tool. You can write it yourself, or just use the tool that I wrote. Anyway, so those are all 5 that are predefined, and this is already pretty good. But what if we want to add something by ourselves? Let's try to do that. So what are one of the most highly requested features of Stream API methods that were never added there? I can think of a few, like, for example, zipping with indexes, or waiting for last elements, or perhaps distinct by. Let's see if we can actually pull that off ourselves. So we have a string. We have a stream of a couple of strings, ABC, and let's say we want to introduce an intermediate operation that zips those elements with their indexes. In the past, you could pull it off. If you had a list instance, you could create a stream of indices, and by iterating stream of indices, access elements of a list and then put them together. That could work, but that's tedious. Let's try to do it by ourselves. So let's write our own first gutterer. And just like you've seen in the past, the API is more or less the same as of collector's API. So what we want to do is that we want to have a gutterer that takes the element t that accumulates this result somehow. At the moment we don't care, but we'll precise it in a second. But it returns map entry with a t and long. Well, and it's going to be called zip with index. And now we need to write our own gutterer. And there are a couple of predefined static methods that make it way easier. So for example, if you start with gutterer, you have a couple of options, off and off sequential. If you are not planning to use your gutterer with parallel streams, then it's very easy choice because you go one of the off sequential ones. And you need an initializer, you need an integrator and a finisher. Initializer, just like with collector's API, is some form of accumulator or a helper object that you use along the way. So in this case, we want to have something that will help us keep track of the index. So we'll just go for atomic long because it's easy and mutable. And now we need to define an integrator. Okay, can you see now? So, and now we need to come up with the integrator. Integrator has three parameters. It has the state object, which is essentially this thing. It has an element, which is the current element that's getting piped through stream, and the downstream, which is essentially the stream, the next steps of the stream API. So what we do, we simply push new map entry with atomic integer in here, and we return true. This is quite an important thing, because by returning true or false, you get to decide whether stream should continue or not. You can essentially short-circuit stream if you return false. This is super interesting because that's something that's not available in collector's API. And that's all. As you can see, this is not very hard. So let's try to use that. So again, let's introduce a stream of some strings. Let's gather zip with index for each and run it. And here we go. So we wrote our first gutterer, which is, and as you can see, there's not that difficult due to a lot of helper methods that are available out there. I can already give you one tip that we could have used here, but we didn't. The mechanics of providing signaling certain characteristics to stream API are slightly different. In collector API, it's this characteristics method where you precisely return a set containing characteristics. And it can be concurrent, unordered, and with identity finish. However, with gutterers, it's not a thing anymore. But what you use instead is a marker interface. So for example, and one of the most important properties that you can configure for a gutterer is whether it's greedy or not. If it's greedy, it means it's always consuming on all elements, which essentially makes returns true all the time. And this is the case here. Since we are zipping with index, our intermediate operation doesn't really make any decision whether to stop processing elements. It just adds an index to them. And the way you do this is that you wrap all of that into a special integrator of greedy. Internally, as you can see, it does nothing. It just returns a greedy instance, and greedy instance is just an extension of integrator. But internally, inside Gutterer API implementation, you can actually see that they check whether instances of gutterers, of integrators are instances of greedy and make some decisions based on that. Unfortunately, you still have this true or false here, but there's not much you can do with it. It just doesn't do anything. So we have our zip with index gutterer. What if we don't want to zip with index, but with another collection? Or an iterator, because that's slightly easier. So let's say we'll have T and T1 and T2. So we collect elements of T1 and we return map entry of T1 with T2. So we have zip with, let's call that iterator. Let's make it iterator because it's slightly easier. T2. Yeah, no iterator, but iterator. Iterator would be a fun thing to have. Anyway, so now, oh wow, that's nice. Let's see if that's correct. So, again, in this case, your intermediate state for the presentation will be an iterator itself, because that's what you are going to pass along the way. And it's going to keep track of the state. If it has a next element, you push a zipped entry containing both elements, and then you return true, else you return false. So if it doesn't have any more elements, you return false. And it makes sense, because if there are no more elements, you don't want to continue the stream, because the second stream is gone. So in this case, it doesn't really make sense to go for the greedy one. You can go for the normal one, and let's try to play with that. So we go for another example, our main, that's going to be 8, 9. We create a stream of 1, 2, 3, 4. We'll create also a list of A, B, and C. Let's call it strings. Those are our ints. We gather, zip with, and provide string iterator for each, so it's C. Let's print it out. And here we go. Second iterator, second getter done. So as you can see, we've already managed to expand our stream API with zipping. Obviously, we can keep going. So for example, if you take zipwith and let's say you don't want to create this extra map entry, you could, for example, have a by function that accepts two entries, T1 and TR, T2, and returns R, that actually processes them somehow. That would look here, but let's have iterator of T2 in here. So now the only difference is that you will be returning an R here. So instead of that, you need to just apply a function to those two elements. And here you go. Another operation done. Let's see that in action. So that's E10, and we zip with string iterator, but we want to manually just concatenate those two. So instead of pairs, now you have strings going through that. So as you can see, it's pretty easy. Let's try to do something else. So one of the most highly requested features was distinct by. What is it all about? Let's see. So imagine you have a stream of strings. A, BB, BB, CCC, DD, EE. So what you can do is you can call distinct and then print them out. However, the problem with that, this is essentially about equality of strings. So this is equals / hashcode verification. So you have two strings called BB and BB, and as you can see, it appears only once. However, there are strings with the same length here as well. What if we wanted to introduce a custom, an ability to perform distinct by property of those objects? If you tried to sort that, you could inject a custom comparator right in there. But you can't for some reason. But I mean, you can for sorted, but you can't for distinct. So, well, we have all the tools that we need to do that, because we have collectors API, we have getters API. Let's choose the right one and implement that. So let's do that. So we write our own new getter, distinct by, and this is going to be a T getter taking T's with some intermediate presentation, returning T's, and we call that distinct distinct by certain property, which we need to define here, TP, key extractor. It's generally a good idea to also ensure that this object is not null. So now we go for gatherers of sequential. So I'm not sure that's. I think it's hallucinating. Anyway, in most cases, if you want to ensure that things are not duplicated, what we do, we use some form of a hash set or a hash map. So we'll introduce a hash set of type P, new one obviously, and now an integrator. So we go for a greedy integrator. I hope you can see that. And now it's very simple, because now we extract a key. We checked whether this was this already existed in a set, and then we push an element or not. And that's all. So let's try to use that. Now we go distinct by string length. So as you can see now, we have guarantees that we have only one element of it. I mean, we have only one string element satisfying this distinction by predefined property. So as you can see, this Gatherers API is pretty powerful, and it gives you now pretty much anything and anything you would ever want to. So you don't need to go to JDK mailing list and complain that there is no method that you would like to use, but you can just implement it yourself. Another idea would be, for example, to implement last one. So we have a way to take first n number of elements. But what if you wanted to take last couple of elements? So if we take stream of 1, 2, 3, 4, you can say, okay, give me max 2 elements. What if I want to have last 2 elements and not first ones? Well, guess what? We need to implement it ourselves. So let's try to do that. Once again, we start with T. We're going to have a gatherer that takes element of T with something in between. And this will be last int size. So what we can, this is again hallucinating. So let's try to do it by ourselves. You will need some form of an array list or some temporary storage of those values. And then you need a integrator, greedy of greedy. Because we are, in order to be able to know last elements, we still need to consume all stream elements. So now you add element if size is bigger than this. Well, let's say it does remove first. It's a bit easier, and you push nothing, because guess what? You are only able to push elements at the very end of a stream. So we say, ignore the downstream altogether, but we'll pipe stream elements in the finisher at the end. So you have state downstream, which is yet again hallucinating. So if the downstream is not rejecting any values, we just pipe it through. And now I have way too many. Okay, it seems to work. So now, if we want to go for the last one, we go gather last 2 elements for each South C. We are missing something here. Too many? Nope. Not enough? Oh yeah. Let's try again. So here's our example. We take last 2 ones, and we got 3 and 4. Looks fine. So as you can see, this is pretty powerful, and I'm very eager to see it GA in March. Actually, I was a bit slightly disappointed with the fact that we only got just a couple of those, because again, this is just 5 gatherers, right? You have fold, scan, fold, which is effectively slightly duplicating reduce functionality. You have map concurrent, scan, window fixed, and sliding. So I figured out why not create some by myself, and I created a library that introduced all the missing ones that you might want to use. I tried as much as possible to not duplicate existing functionality, because that's what I see a lot online. So when a new API was introduced, everyone tried to re-implement everything using gatherers. It doesn't always make sense, so I tried to focus on those that are effectively missing. So some form of filtering by indexes, distinct by until changed, sampling, or form of zipping, and missing window operations with dedicated steps. This is all available at, this is all called, where is the main one? This is all called, you can find this on GitHub. It's called More Gatherers, and will be released as effectively on the same day when the new JDK goes live. So that's all what I wanted to show you today. I hope you are as excited as I am when it comes to gatherers, and it seems like we have just a couple of minutes for questions. So thank you a lot, and I hope you've learned something. Thank you.